class, Professor Smith here. So excited to create a video on word problems involving optimizing area by using a quadratic function. And this is actually number 7 from sample test 2A. In this example, we have a wire that's 24 centimeters long, as shown below. The wire is cut into 2 pieces, and each piece is bent and formed into the shape of a square. Suppose that the side length in centimeters of one square is x, as shown below. Part A asks us to find a function that gives the total area enclosed by the 2 squares in terms of x. Part B asks us to find the length x that minimizes the total area of the 2 squares for a length x. And whenever we ask to minimize or ask to maximize, as in the other 2 examples, that's where we're optimizing area. And part C says, what is the minimum area enclosed by the 2 squares? In other words, once you determine that value for x for the first square, that means you can determine the value for the side length of the second square, which may be the same. And once you know those 2 side lengths, then you can find the 2 areas. And we're going to find out something really cool when we look back at A of x. So let's go ahead and begin. Whenever you have an optimization problem, you're always going to have some kind of constraint. In other words, if I took away the portion of the problem that talked about the wire being used was 24 centimeters, if I took that away and just said, okay, give me the area of 2 squares. You could say, well, one square could be 10 by 10 is 100. Another square could be 5 by 5, and that's 25. And I say, okay, well, give me one that's smaller. And then you can say, well, how about one that's 9 by 9, which is 81, and this one's 5 by 5. Since 81's less than 100, this is smaller. Another example could be 7 by 7, and this one be 5 by 5. So you can see that if I don't have some kind of constraint, then you can say, well, the one with the least area is just the one where you have no squares at all, 0 by 0 and 0 by 0. And so this constraint of 24 centimeters is letting us know that, yes, there's different values that we could, or ways we could cut this wire, but however, there is one way that will give us a minimum value, and it is tied to the area formula that we're going to come up with, woohoo, which has some special features, which we'll share in a minute. It turns out we don't know the side length of the second square, so I'll call it Z, if that's okay with you, and I'll label it in purple. And if I want to take this wire that's 24 centimeters and form it into these 2 lengths, which this distance around is going to be x, x, and x, which is 4x. And similarly for the second square, which I'll label with the side z, that's going to have the distance around or perimeter of 4z. And I know that my wire length is 24, so these 2 distances, 4x and 4z, has to equal that total wire length. So I know that 4x plus 4z is equal to 24, and that's my constraint. So I also know that the area of a square is equal to length times width, but for a square, the length and the width are the same, so it's really just x times x. So the area of a square is just the side length squared. So for our first square, the area is going to be given by x times x, which is x squared, and then for the second square, it's going to be z times z, and then we're going to add up those 2 areas, plus z squared. So now I have a formula for area, but we notice that our formula for area has 2 variables, x and z, and our problem asks to find a function that gives the total area a of x. In other words, it's not a of x and z, where a of x and z is equal to x squared plus z squared. That's true. That's the formula for the area. However, they're asking us to give the formula in terms of 1 variable. So how do we do that? How do we change this so that it only has x's in it? Well, that's where we use the constraint. If we divide both sides by 4, because I noticed that 4 goes into 24 as well as to itself, then we're going to get x plus z is equal to 6. Solving for z, and you say, well, why do you want to solve for z? Because I want z in terms of x. So if I isolate z, then I'll have that. So I'm going to subtract an x from both sides. On the left, it cancels, and on the right, I'll have 6 minus x. So now my area formula, which was equal to x squared plus z squared, is now equal to x squared plus 6 minus x quantity squared. Now I have a formula, a of x equal to x squared plus quantity 6 minus x squared. So now we've completed part A. It's equal to x squared plus the quantity 6 minus x quantity squared. Now ALEKS will accept the answer even though this isn't necessarily combined with like terms, because we could expand 6 minus x quantity squared, and then that will give us an x squared term, and we can combine the first x squared plus the other x squared. So we could simplify this further, but ALEKS will accept this answer. But it turns out, since you're going to have to simplify it anyway, you can put that answer in as well. And you say, well, why do I have to simplify it anyway? Well, in part B, they ask us to find the side length that minimizes the total area of the two squares. And in order to find that side length, we need to find the x value of this quadratic function. In order to find the x value that minimizes the total area of the function, that's equivalent to finding the x value of the vertex. And we use the formula x equal to the opposite of b over 2a. And that's why we need to expand our formula for a of x to find the values of a and b. However, the way that we have written our quadratic equation, it's not in the form where I can determine what a and b are. So let's go ahead and simplify a of x so we can use this formula to find the x value of our vertex. Another question might be, well, how do we even know that the x value of our vertex is going to give us a minimum value? Let's go ahead and expand so we can see why. So we can start by simplifying our expression by expanding the binomial 6 minus x squared. We can rewrite it as 6 minus x times 6 minus x. Or we can use the formula that I thought, well, you know, it's a good idea to memorize this rather than to write it out each time. So you can do 6 minus x times 6 minus x and FOIL it out. Another way is to remember that it's going to equal 6 squared, that's the first term, which is 36, minus 2 times 6 times x, and 2 times 6 is equal to 12, times minus x is going to give us a negative 12x, plus the last term squared. The opposite of x, or a negative x squared, is going to give us plus x squared. So that's what's going to happen when we expand the binomial. Now we can combine like terms. X squared and x squared gives us a 2x squared. Writing in descending powers, I'm going to write the negative 12x next, and then plus 36. Now that it's in this expanded form, I know what letters A, B, and C are. A is equal to 2, and B is equal to negative 12. C is equal to 36, but we don't need that constant to find the x value of our vertex. So x is equal to the opposite of B all over 2a whenever we're trying to find our vertex. So we take the opposite of negative 12 all over 2 times 2, which is 12 over 4, which is equal to 3. So that gives us the value of x that will minimize. So why is that again, that that's going to minimize? When we look at our quadratic function, we see that the leading coefficient is 2. That's the coefficient of 2x squared. So since that leading coefficient is 2, in other words, a is 2, and a equal to 2 is greater than 0, which means it's positive, we know that our parabola is going to open up. So if it opens upward, we can see that its low point is going to occur at the vertex. And that low point is the minimum. So whenever you open up, you have what we call a minimum. If the graph opens downward, then you're going to have a maximum. So far, we have that a of x is equal to 2x squared minus 12x plus 36. And we have that the side length of x equal to 3 centimeters will minimize the total area of the two squares. Part C asks, what is the minimum area enclosed by the two squares? Well, what's nice is Part A gives us a general formula for finding the area of the two squares if you know the x value of the first square. So since we know that the x equal to 3 is the value that minimizes the total area, When we substitute in x equal to 3 into our equation for area, that's going to give us the value of the area that is minimum. So let's go ahead and evaluate. A of 3. So A of 3 is equal to 2 times 3 squared, replacing x equal to 3 in the first term of our quadratic, minus 12 times 3 plus 36. Since we're able to use the ALEKS calculator for this problem, we could just substitute this value into the ALEKS calculator. Since the numbers are relatively small, then they're not a little odd like 47, which I would not be able to do very quickly in my head. I would definitely use a calculator, but for this one we'll go ahead and do it without the calculator. So we'll get 3 squared, and 3 squared is 9, and 2 times 9 is 18, minus 12 times 3, and 12 times 3 is 36, so it's minus 36 plus 36. And we see that the subtracted 36 and added 36 cancels, and that leaves us with 18. Because our dimensions were, the area was squared, then we know that it's going to equal 18 centimeters squared. And I think on ALEKS, you just have to put in the 18. They give you the square centimeters. I should also point out that you could also use the first area formula that we had, which was A of x, which was equal to the first square, which was x squared, and then the second squared, which was 6 minus x squared. So if you compute A of 3, you'll get 3 squared plus 6 minus 3 squared. So you'll get 9 plus 9, because 6 minus 3 is 9. 6 minus 3 is 3, and when you square it, you get 9, and then 9 plus 9 is 18. So you get the same value, and in fact, this one's easier to evaluate if you didn't have a calculator. So graphically, what does this look like? So here's the graph of our parabola with the vertex 3, 18 shown, and then I evaluated the area at 1, and I got 1 squared plus 6 minus 1 quantity squared, or 1 plus 25, which is 26. So here's the ordered pair 1, 26, and because of symmetry, if I'm 2 to the left of 3, which gives me 1, 2 to the right of 3, which gives me 5, we'll have that same y value of 26. So there's my parabola. What this graph is really telling us is if you give me a side length x, which is the length of the first square, any point on this graph will give me the area for that corresponding height. So for example, at x equal to 3, I have a height of 18. That lets me know when x is 3 centimeters, that my area is 18 square centimeters. So we can think of this y value, or this y-axis, as the area for any point x on our graph. So when x is equal to 1, then the area is going to be given by 25. And when x is equal to 5, the area is also going to be 25. To summarize our steps, we use the constraint to write the area function in terms of one variable. To find the x value that optimizes our area function, either minimizes it or maximizes it, we always find the vertex. So we find the x value of the vertex using the formula that x is equal to the opposite of b over 2a. For step 3, we're going to find the optimal area. That is the area that either minimizes or maximizes our area function by evaluating it, a of x, when x is equal to the opposite of b over 2a, or finding a of the opposite of b over 2a. So I hope this video on word problem involving optimizing area by using a quadratic function has been helpful for you.